Continuing our studies or discussions on substitution reaction with alkyl halides, one of the most important reagents or reactants that are seen in substitution reaction are nucleophiles. First, what are nucleophiles? Nucleophiles are substances that have a pair of electrons. It could be as lone pair in the species we are looking at. It could be part of a pi electron. For example, any electron-rich double bond can act as a nucleophile, and some of them are fully negatively charged nucleophiles that can react in this substitution reaction. So the substitution reaction goes if you have an alkyl halide, a nucleophile with a pair of electrons comes and hits that electrophilic carbon, right? This is seen negative. So that nucleophile hits the carbon and makes a new bond. That's alkyl nucleophile bond. And the leaving group goes with pair of electrons. So this is how the reaction goes. For that, you need nucleophiles. As I said, nucleophiles can be with a pair of electrons, like ammonia here, for example, which has a lone pair of electrons on it, can be used as a nucleophile. Part of a pi electron, for example, if you have an electron-rich species like this pair of electron is a part of pi system. For example, if it has CH3 again here, this pair of electrons in the pi system can be used to attack that carbon because this is electron rich. So when you say part of a pi electron system, even a double bond, if it is rich, we can use it as a nucleophile. And the fully negatively charged is like cyano group, cyanide minus. That is, for example, if you have sodium cyanide, forget the counter ion sodium plus, that's how we introduce cyan nucleophile. So that would be acting as a fully negatively charged nucleophile. Lone pair is phosphine, for example, type reagents with pair of electrons on phosphorus, and a thiol-derived sulfide, metal sulfide, can be also used as a negatively charged nucleophile. So the most important thing to consider is the substitution reaction per se is actually an acid-base reaction, meaning that the nucleophile is like a loose base. This is another way of looking at it. And the electrophile, the alkyl halide, which is used as an acid. So basically, this is an acid-base reaction. Also, if you're just looking at it from a different perspective. So a nucleophile with a pair of electrons would interact with the electrophilic carbon because it's electrophilic, because that the carbon halogen bond is polar bond. Most of the electrons are withdrawn or carried by the leaving group. So obviously, this is also an important counterpart to consider, how easy that leaving group also departs or breaks away is an important factor consideration or in the substitution reaction. Here I have a bunch of substitution reactions. One thing I want to comment is all of these alkyl halides given here are primary. This is metal halide, sorry. This is a metal chloride, so it's not, we don't call that primary, that's metal chloride. This is a primary iodide. This is a primary as well, because it's on this carbon is a halogen is attached. This is a primary as well. This is, all of these are primary alkyl halides. So the nucleophile, our interest here is a hydroxide ion, anion, which is a negative charge. It's derived, for example, it could be from sodium hydroxide, or it could be even derived from potassium hydroxide and the like. So basically, it is a very strong nucleophile where it has a pair of electron fully charged electrophile. So it kicks the carbon here, just like this, and makes the methanol. That's a new bond. Carbon-oxygen bond is formed. Chloride is living as a living group. Here is a thiol. Usually it comes as sodium sulfide or sodium counter ion. So you can just get it if you just look at this. This is what that reagent is. Full negative charge. This is on sulfur. Sulfur is a good nucleophile. So the living group here is an iodo. This is iodohalide, propyl iodide. So this carbon is what it's interacting with. So this is a fully charged nucleophile, a strong nucleophile as well, sulfur derived. This is a methoxide anion. Methoxide because it's derived from methanol, if you just look at it. So that methoxide has also a very nucleophilic electron-rich oxygen, which can hit that carbon and replacing the bromine group. And making here, this product is an ether functional group because you have an alkyl group and oxygen and another alkyl. So it's R, O, R prime, which is the CH3. So this is ether. So ethers are formed by nucleophilic substitution of an alkyl halide. So that's how you make an ether. Here you have made a thiol by replacing the iodo using a nucleophile. Here you have a lone pair on nitrogen. So this is not fully charged, but we are using the lone pair on nitrogen. Those are available. So those lone pairs, if it was on oxygen, for example, the lone pairs would not be that available. But nitrogen lone pairs are not highly attached. They can participate in the nucleophilic displacement of the PR. So that's a lone pair of electrons participating as a nucleophile. So here also pyridine is a base. Pyridine is a base. Like this is also a trimethylamine is a base. This base, using its lone pair of electrons, would participate in kicking out this bromine. So that would make a pyridinium. This is a hexyl bromide, a primary, because this carbon is only attached to one other carbon. So it's a primary. Mind you, here the classification is important, that now what you see, all of this are primary. This is, of course, methyl halide, methyl chloride. This is a primary. All of them are primary. The reason why I'm emphasizing this is when we go deeper into the mechanism of the reaction, the type of alkyl halide you have also determines whether that substitution goes in one step or two steps. So it's very important to note that these are all primary examples and these are nucleophiles. So coming back to as a summary, nucleophiles are species or entities with pair of electrons, like one of those. And you could be part of a pi electron. If you have an electron-rich double bond, it could use that double bond to heat that carbon. A fully negatively charged ones, like cyanide group and hydroxide ion, ethoxide, and methoxide, all these are nucleophiles. So as you practice more in just doing more substitution reaction, you will find out all the nucleophiles either carry a pair of electrons, maybe carry lone pair, maybe they have a very rich pi bond in their system. So with this, we'll just move on to see also some of the characteristics of a living group, because that also is important in the substitution reaction. There are good living group and there are bad living groups that the reaction could not go as maybe shown or indicated. So the next section would be just to show you what is the characteristics, or what are the characteristics of a living group. There are many factors that affect substitution reaction. So one important factor is how strong is the nucleophile. Second, how stable or how the living group acts once it's participated in the reaction. So a good living group is something that carries a negative charge very nicely. It could be by the resonance or by its own inherent electronegativity to carry that charge. So we'll continue with a kind of living groups that are good for substitution. Just finished talking about the nucleophiles. Now we'll move on to talking about living group in substitution reactions. So as I already mentioned, the alkyl halide would be attacked by a nucleophile. The R nucleophile new bond is formed, but here there is an important counterpart, the living group. So what is the living group that makes this alkyl halide nucleophilic substitution reaction to go much easier? So what's a good living group? A good living group should be a weak base. When we say it's a weak base, it shouldn't highly be bound to the alkyl. That means if it is weakly basic, that means the acid-base reaction is not that strong. That means that it could be a good living group. That's another way of looking at it. So important thing for a living group is it has to be a weaker base. When it leaves, we should check that it is a weaker base than the other group you are comparing with. And it should stabilize the negative charge, meaning that since you are generating X minus or the negative charge at the end of the reaction, if it could be something that stabilizes the negative charge better, it would be also a good living group. Here I have brought some examples of fluoride, chloride, bromide, iodine. If we just compare this, which one would be a good living group, the way we have to check this would be which one is a weaker base. So if you just look at their acidity, HX, meaning that a strong acid would give a weak base. That's why we are trying to see what their acid looks like. So HF is the acid, HCl is the acid for this, HBr is the acid for this, HI is the acid for that. So if you just look at the strength of the acidity from what previously we have seen, the HF bond is very strong, therefore it doesn't give easily the proton. So the acidity actually increases this way. So HF is weak acid than the HCl. HCl is a weaker acid than HBr, and HI is the weakest of all the series. So HI is weakest acid, right? Oh no, I'm sorry. HI is the strongest acid. Sorry. So HI is strongest, and HF is the weakest acid. The reason I brought this comparison is that the weakest acid would give the strongest base. You don't want that. Therefore, F would not be a weak base. That means it's not a good living group. So HI, when it's dissociating, it gives you I minus. That means the strongest acid, HI, when it dissociates, it gives H plus and I minus. The strongest acid would give the weakest base. So what we have said is you need a weak base to be a good leaving group. Therefore, I minus is the best leaving group than F minus. But bromine is much better than fluoride. So the leaving group ability increases this way. So fluoride is not a good leaving group. Fluoride a little better than fluoride. Bromine is a little much better than chloride, and so on. So the weakest the base, meaning the weaker the base, the leaving group as a base, the better for as a leaving group. That's what it means. For example, if you just look at hydroxide, OH minus, versus water. So the basicity obviously is, this is strongly basic. OH is very strongly basic than water, obviously. So this is much less basic. So as a leaving group, OH is not a good leaving group, but water is a good leaving group as compared to OH minus. So that's how we compare them. The stronger the base, as a base, that X minus, the weakest as a leaving group. So you don't want that in your alkyl halide as a leaving group if you want to have a successful substitution reaction. So in alkyl halide, for example, if I have alkyl iodide, alkyl bromide, even alkyl chloride, those can be a good leaving group to give you a best reaction. So, but if somebody gives you among this series which alkyl halide you want to use as a reactant, you'll use the best will be alkyl iodide, alkyl bromide, and so on. So the stronger the base, as a base, if this is a very strong base, that's not a good leaving group. So you don't use that as a leaving group or as alkyl halide to start with. So here I have a list of basic substances here. You have amide, hydride, hydroxide, fluoride, iodide. So this is also one of the basicities. The basicity, of course, increases this direction. Basicity, the strongest base and weakest base on the bottom. So you don't expect amide, NH2R, NH2 to be a reaction that you could do or replace by a nucleophile because it's a very strong base. That's not a good leaving group. Hydride is not something you can replace with a nucleophile. Hydroxide is not something you would recommend or suggest as a leaving group. So fluoride, if we compare them with this, fluoride is also the weakest and it's not a good leaving group. So iodide in this series, the weakest even in this series, would be something you would be using as a leaving group. So the most important aspect of a leaving group is that it has to be a weakest base. When after it's left, it should be a weakest base. If it's not a weak base, it's less likely that it would leave the alkyl chain. That's the principle, or that is the idea we have. It cannot be replaced by a nucleophile coming in attack to kick it out. So a weaker base is a good leaving group. So this is the general conclusion. The weaker the base, the better as a leaving group. Here I have two examples. So these are like problem exercises we can just use. So this is amide. Amide is, this is ethyl amide because 1, 2 carbon, and this is obviously a primary carbon. So would you expect amide to be a good leaving group? Obviously, from what I already told you, that will not be a good leaving group. because that is a very strong base by itself. Okay, so the other way of looking at this would be if we have to compare bromide versus amide to just see what their acidity is. So NH3, for example, the acid 4, and that is HBr is its acid form, and see what their conjugate looks like. So obviously ammonia is it's not basic, it's a very weak acid. It's a base, therefore it will be very, very weak acid. So what it generates is a very strong base. So actually your HBr is relatively very acidic. It's very acidic. It would give H plus and Br minus, and it gives weak base. So this strong base cannot be replaced or acting as a nucleophile here. This is as a living group. This reaction cannot happen. That means the bromide anion as a nucleophile would not replace the amide group. As you see, bromide actually is somewhere here as a living group in between here. So even if it acts as a nucleophile to do this, there is no way that reaction would happen. Okay, so in the next reaction, let's see these two comparisons we have. You have an iodo-alkyl halide, and you have a nucleophile, a cyanide nucleophile. Let's see what this reaction looks like. Okay, the HI, the acid form of this thing, is just for us to know what kind of base that is. So HI is a very highly acidic because pKa is -10. That means HI is very acidic. So it gives H plus and I minus. So if this is strong acid, the conjugate base is weak conjugate base, weak base. But if you compare HCN, HCN is a very weak acid. Therefore, CN, when it's generated, HCN, H plus CN minus. So what it means is the hydrocyanic acid, when it gives you H plus and CN minus, it's not giving you a weak base. It's giving you a very strong base. This is strong base. Strong base. Therefore, a strong base, okay, a strong base would kick out a good living group. So this reaction can happen. So the cyanonucleophile can kick out the iodo living group. So iodine here is a good living group. So the reaction would go as a substitution reaction and can happen. So this is the logic how you'd examine different living groups. They have to be weak bases when they left. So iodine minus is weaker base than the cyano. So cyano is not now it's a stronger base and it's a good nucleophile in this case. So as I already told you, nucleophiles have a pair of charges on them, pure negative charge. So rather cyanide, because this is a CN nitrile group as with a negative charge, is a good nucleophile, and you have a good living group. This combination is good living. The iodo is a good living. So the combination of this reaction to give a substitution reaction with a cyanide group would be a very successful substitution reaction. So the top is not successful. This comes in the indicated direction. So bottom line is that a weaker base is a good living group. Second, we have to also consider that if that negative charge after it left is, if it can be stabilized, that's a good leaving group. When we say stabilize the negative charge, if there is a resonance, for example, if something left and you have a resonance that can be drawn for that negative ion, that is a best also leaving group. So in the future, we'll be doing some exercises where you have to compare their acidity and what the conjugate base would be. So that's a strategy how you'd determine whether a leaving group is a weak base or a strong base. If it is a strong base than the nucleophile, that reaction would not happen. So it should be a weaker base than the nucleophile. The nucleophile should be stronger base than the leaving group. That's the point. Here, the nucleophile, a strong base than the leaving group, a good leaving group, because it's a weaker base as I minus. So I minus is a weak base, and Cn minus is a strong base. So this is a good combination. You have a weak base as a good leaving group and a strong base as a nucleophile. This is a good combination to effect a substitution reaction. So we'll continue to see the comparison of nucleophilicity versus basicity. So this is also another important concept. Students get a little bit confused when we say a good nucleophile and a good base or a strong base. Both are sometimes, the good nucleophile could be a good base, but a strong base not necessarily would be a good nucleophile. This is the point we want to understand in the next section. A good nucleophile could be a strong base, but not all strong bases are good nucleophiles. Okay, here we discuss about nucleophilicity and basicity. Actually, they go hand in hand. The stronger the basicity, the stronger the nucleophilicity. So, but there are some distinction we'll discover later on when we go deeper into the mechanism of substitution reactions. Obviously, you have full charge hydroxide anion, which is a good, strong nucleophile. So this is strong base. Also, it's a strong nucleophile. So if you just look at this acetate anion, which has a negative charge, versus the hydroxide ion, if you were to compare these two as a nucleophile, obviously this will not be a good nucleophile because it's not also a strong base. So the conclusion is the stronger the basicity, the stronger the nucleophilicity would be. Here, as you just look at here, this lone pair of electrons on the oxygen are not as available as the ones which are on the hydroxide. The hydroxide anion have a pair of electrons that are not resonance stabilized, so they are not available, that are available for electrophilic attack. But here, this acetate anion does a resonance stabilization, meaning that the anion is stabilized rather than going and attacking by just pushing this electron back here, pushing here. That negative charge is delocalized by a resonance structure. And this. So that electron pair is actually shared by the two of the oxygens. Hence, it's not very available to go and do an electrophilic attack on another carbon or alkyl halide. So if you were to compare this OH minus versus acetate anion, this is less basic because the lone pair of electrons are resonance stabilized. They don't have a potential to go to do other reaction. Rather, they could be delocalized over the same system. So less basic, less nucleophile. Because the oxygen actually holds back the electrons to itself because it has another way of delocalizing these electrons by resonance. So this is resonance stabilized. Resonance stabilized. So it's not very available. That's why it's a less basic and less nucleophile. So far our conclusion is the stronger the basicity, the stronger the nucleophilicity. Okay, let me come and also show you here. Here you have an etoxide. Here you have a third betoxide anion. Both are nucleophilic, as you see. They have lone pair of electrons, lone pair of electrons, but there is a little bit slight difference. Even just looking at them, the size is different. So this is actually, this alkoxide is on a tertiary carbon, one of the differences. This alkoxide is on a primary carbon. Okay, that's fine. Let's see the strength of their basicity from their pKa value. pKa 16 is for the alcohol of this. So if you are to see CH3, CH2OH, pKa is 16, meaning that the acidity of this proton is pKa value of 16. Versus if you just look at this, the pKa value for that alcohol, that hydrogen, is 18 as given. So which one is a stronger acid? The stronger acid would be this. Just by order of 2 magnitude, this is more acidic. This proton is more acidic than that proton. So just by acidity, the conjugate base is, this is a stronger acid. So the conjugate base of this is weaker. So it is a weaker base. That is just a comparison, weaker base. So this is a weaker base. Weaker base. Because it's stronger acid than that one. It's a comparison. So this becomes now is stronger base. Stronger base. So here is very important idea that now from this. This are in terms of nucleophilicity, you would just say, oh, this is a weaker base, so it will not be a stronger nucleophile. But this is stronger base, but it would be a better nucleophile. Here, it's not the case. You should be careful because nucleophiles also want to access the alkyl halide, right? They go back to the alkyl halide. The nucleophile comes at the back of this, kicks out that, and pushes that out. For that, the sterics, the mass, also determines how nucleophilic a substance is. So actually, even though it's a weaker base, this is a better nucleophile. Small and not branched, it can access easily to attack the electrophile, better nucleophile. We are not saying it's not a stronger base here. So necessarily stronger base is always a good nucleophile. Size also is very important in terms of determining. This is very branched and it has a bulky group on it. This is bulky, this is bulky. As a base, it's good, but not a good nucleophile. So you have to always be careful. A stronger base is stronger nucleophilicity. But in some instances, even though you have a strong base, if your mass or your size is bulky, like tertiary butoxide, like that, this is tertiary butoxide, tertiary butoxide is a stronger base, but cannot be a good nucleophile. These are the distinction I want to highlight here. Always good nucleophiles are stronger bases, but not all stronger bases are good nucleophiles. That's a very important distinction you have to make, because if it is a stronger base, but if it is bulky enough to access and hit this carbon, this will take some time and also some energy barrier. So this will not be a good nucleophile. Rather, it acts as a base. That's why now in a substitution reaction, substitution and elimination are always competitive, meaning that based on your condition, what nucleophile you have and what living group you have, either the nucleophilic substitution can happen or the base elimination reaction can happen. So when you are using a nucleophile like this, I mean, assuming that you are running a substitution reaction, if you use this kind of alkoxide, butoxide in your system, it rather acts as a base than just kicking out that X. So it doesn't do that. So it rather acts as a stronger base. So it does elimination than substitution. This is a point. So your condition is important, whether you would effect substitution or elimination. So for good substitution, you should have a good living group and a good nucleophile. But if you have for example, for this case, even though your living group is good, if you are using such kind of stronger base, it rather do elimination. The base acts as taking as that proton, this pair of electrons come in, this goes in, so it forms elimination product, which is double bond. This is not what you expect. If you do substitution, that's not what happens. Substitution just replaces X with a nucleophile. So the conditions of the reaction is important. From now on, when we do exercises and problem solving, you have to understand whether that particular reagent is for nucleophilicity or basicity. Based on what nature it has, that's how it works. So this is a good nucleophile, but a slightly weaker base than that. So not always stronger bases are good nucleophiles, but rather all nucleophiles are stronger bases, or they're basic. Okay, as I said already, this is already what we have discussed. A stronger hydroxide anion is much better than water as a nucleophile. So this is a strong base and a strong nucleophile. This is also, the size is very limited, small, so stronger base and a good nucleophile as compared to ammonia and water molecule. So that's how you would be comparing nucleophilicity versus basicity. So for nucleophilicity, it's not only going and substituting the nucleophile, you have to approach the alkyl halide. That means your sterics, your mass should be appropriate enough, like smaller enough to reach to the alkyl halide from the back. Usually it happens by backside. So that approach by the nucleophile should be much easier. So all strong nucleophiles are strong bases, but not all strong bases are good nucleophiles. That is the conclusion we have on this. So in the next lecture, we'll be discussing about different kind of conditions and different solvent systems, what solvent we use to dissolve these reagents, and effect whether we do elimination or nucleophilic substitution. Also depend on how fast it goes, depends also on the type of solvent we use for our substitution reactions. So the next lecture would be on several conditions of the reaction for substitution.